Thank you very much for joining this talk about AB Linux updates with RAUC and meta-rauc community, now and in the future. My name is Leon Anavi. I'm a senior software engineer at Konsulko Group. This is a services company specializing in embedded Linux and open source software, providing hardware and software services for build, design, development, and training. And my colleagues and I have upstream contributions to various popular open source projects, including, of course, the Yocto Project and OpenEmbedded, automotive-grade Linux, Buildroot, U-boot, the Linux kernel, as well as technologies for software over-the-air updates, such as Mender, OS3, and RAUC, which is part of the topic today. The company is based in the United States with an engineering presence worldwide. I'm personally working remotely from Plovdiv, Bulgaria. The agenda for today starts with RAUC. And actually, this is a sequence to a talk that I did a year ago about using RAUC with a Raspberry Pi. And today I would like to show you how this has progressed over the time. But if you're not familiar with RAUC, don't worry, because we'll start with a brief introduction to RAUC. After that, we'll have a look at the steps for integrating RAUC on a new hardware. We'll speak about the Yocto OpenEmbedded layer meta-rauc community, which provides some examples. And finally, we'll wrap it up with conclusions, and hopefully there will be time for Q&A. In the meantime, I'm in RC, so right after the presentation, you can ask me anything in RC. Okay, so RAUC is a lightweight update client that runs on embedded Linux devices and reliably controls the procedure of AB updating the device with new firmware revision. RAUC provides a tool for the build system to create, inspect, and modify the so-called update bundles. And speaking about RAUC, over this presentation, you hear a lot of times two keywords. The first keyword is slots. The slot is pretty much anything that can be updated with RAUC. In most of the cases, it's a disk partition, but it could be a physical device or even just a file. And the other important keyword in the RAUC ecosystem is bundle. The update bundle is the artifact that's downloaded on the embedded device and installed as an update. One of the benefits of RAUC is that it uses cryptography to sign these update bundles. RAUC is not only compatible with the Yocto Project and OpenEmbedded, but also with PTXdist and Buildroot. The project was started in 2015 by Pengatronics, and since then it has been adopted by both the community and the industry. The first time when I heard about RAUC was at a presentation during FOSDEM. Actually, I'll share a link to it at the end of my presentation, and I've been using RAUC for the past about 2 years, I would say. So how does RAUC work? So the first thing, on the first image here, we have an embedded device that has been booted with working with the A partition. The A and B partitions should be identical. Of course, there could be far more sophisticated use cases, but the most common way to use AB updates is to have two identical partitions, let's say A and B partition. So at the beginning, we have the device working with the A partition, everything is okay, but at one moment we need to download and deploy an update. The first thing is to download the update bundle, and after that to install it. Once this has been done, we need to reboot the device, and the bootloader should take care of switching from the A partition to the B partition. The B partition is the new partition on which we have installed the update bundle. If everything is okay, the device will continue using this B partition. If the update fails, the bootloader should take care of switching back to the A partition. So in a nutshell, this is how RAUC works with these A-B partitions. RAUC is a project that contains several key components. First, of course, is RAUC, the client that's running on the embedded device, which is written in the C programming language. It's available under LGPL license. All these components are available in the GitHub organization of RAUC. They have different licenses. The Yocto layers, meta-rauc and meta-rauc community are under MIT license, and there are other components for integration with hawkBit. hawkBit is a project of Eclipse. It's a domain-independent backend framework for rolling out software updates to constrained edge devices, as well as more powerful controllers and gateways connected to the IP-based networking infrastructure. The hawkBit is not running on the embedded device. It's actually a server software that's running on a powerful server. That's why it's written in Java. It's also available as source code in GitHub under EPL license. It's a fully open source project as well. It's compatible not only with RAUC, but with other technologies such as SW Update. Basically, the idea is that Eclipse hawkBit is the open source solution which allows engineers to control fleet of connected devices and update them as groups see what's going on with these devices. You can learn more about Eclipse hawkBit at eclipse.org/hawkbit. And some of you might be wondering, are there any alternatives? Is the only solution for updates RAUC? Of course not. Actually, the software over the air update solutions topic is very, very popular in the past several years, almost a decade now. And there are so many good open source solutions to do software updates nowadays. At Konsulko, we quite often use Mender. Mender is also doing AB updates. SW Update is also a popular solution for AB updates. There are solutions based on containers, and there is a whole group of solutions based on primarily on OS3, which is doing like Git for file systems. And OS3 is something that has been initially developed for desktops, but after that was ported to embedded devices. I was, as part of my job at Konsulko, I was involved in this process in integrating OS3 initially in meta updater layer. Actualizer Lite depend on OS3. The same is valid for Qt, OTA, and Horizon. Basically, we can group all these open source products for updates in 4 different groups. The first group is about AB updates with dual redundant scheme. A good example about this is RAUC as well as Mender. I've already explained how it works. The other group is for the Delta updates. This is the things that are done with, for example, OS3, where we have a very small chunks of updates that are installed on the embedded devices. We also have container-based solutions for updating, and we have combined strategies. The combined strategy is something interesting because it allows us to build a base OS with AB updates using, for example, RAUC or Mender, and have Docker running on top of them to manage containers. It's of course not only Docker, because we have the Yocto OpenEmbedded layer meta virtualization, which provides support for building Docker, Xen, KVM, and all associated packages necessary for constructing an OpenEmbedded based virtualized solutions. So let's have a look at the Yocto layers required for building RAUC. The first layer is meta-rauc. This is the layer which provides the recipes for building the RAUC client, which is installed on the embedded device, and all related dependencies. The other layer is meta-rauc-community, which is a layer for providing examples for integration of RAUC, very basic examples actually, on popular embedded development boards. This is a layer which idea is to help you get started quickly. meta-rauc supports all recent releases of the Yocto project, including the long-term support releases, which were discussed by Trevor and Nico in the previous presentation. It's available under MIT license. It's part of the RAUC organization in GitHub. As of the moment, there are 33 contributors, and Enrico from Pengatronics is the leading contributor, and he's also co-maintainer with Jan Lube. And meta-rauc-community is a layer which actually I have created in 2020. The idea here is to provide sublayers with example integrations for popular development boards. The first board which was ported was Raspberry Pi. I've created this as part of, I've explained this as part of my talk last year at the Yocto Summit, so I won't go into too much details, but basically the Raspberry Pi is the most popular single board computer out there, so it was a natural thing to have a simple way how to demonstrate how RAUC works on it. After that, new things were added to the layer. I have to say huge thanks to Jan Lube, who contacted me, and we moved this layer to the RAUC organization in GitHub. This way it's more visible for the community. And I'm happy to say that it has been adopted by the community, and there are a lot of community contributions. In the past year, the layer gained support for QEMU, for Allwinner, sunxi devices, and recently, as part of my preparation for this talk, I've ported it to NVIDIA Jetson platforms. Actually, I've ported it only to NVIDIA Jetson TX2, but it's a similar approach for other Jetson devices. I have to highlight that each of these sublayers in meta-rauc community depends on the BSP layer for the specific hardware. For example, for Raspberry Pi, we're using meta-Raspberry Pi, meta-sunxi for Allwinner, and meta-tegra for NVIDIA Jetson platforms. Meta-tegra is a very well maintained layer, and I believe in the previous edition of the Yocto Summit, Mats Madison, the maintainer of meta-tegra, had an excellent talk. So basically, meta-rauc community relies on both meta-rauc and the respective BSP layers. So the contributors are not so many for meta-rauc community. It's a relatively new layer, and part of the goal of this presentation is to encourage more people to join our community efforts and to port RAUC to more devices. This was started last year. This year it was moved to the RAUC GitHub organization. So far we have 5 contributors. Some notable contributions. Mitch Gaines added support for sunxi boards. These are the Allwinner boards. I'm personally attached to them because a company from my hometown, Plovdiv, Olimex, is famous for making open source hardware with Allwinner systems on a chip. So Mitch Gaines made this enormous effort. He pushed GitHub pull request, which was merged, and now we have an example of how to use RAUC on devices with Allwinner system on a chip. Enrico added support for QEMU, and as I mentioned recently, I've added support for Tegra, which we'll speak in more details about in the next slides. No matter what kind of hardware you are using, there are certain integration steps that you should do for RAUC. So first, we need to select an appropriate bootloader. We have to enable SquashFS in the Linux kernel configuration. The file system must be ext4 because RAUC does not support ext2 or ext3. We have to create specific partitions that match the RAUC slots. For example, the very simple scheme that we've covered at the beginning of the presentation with only 2 redundant partitions, A and B, we have to create them to make sure that they have the same sizes and to configure them as RAUC slots. Of course, this is just for example, but in a real-world environment, most probably 2 partitions won't be enough, and quite often systems need a data partition to store data which is persistent over updates. After that, we need to configure the bootloader environment and create a script to switch between the RAUC slots that we have created on the previous step. Finally, we need to also create a certificate and a keyring and to describe them in the system.conf for RAUC. Here's a very quick example how to build a minimal image of Pocky using RAUC for Raspberry Pi 4. The example is using the layers for the long-term release of Yocto Dumfell. Thanks to meta-rauc community, it's a straightforward process. Minimal things have to be configured. As you can see, we're just cloning the source code, initializing the build environment. After that, we need this step to add all related layers to bblayers.conf. And finally, a few very basic configurations in the local.conf just to specify the machine we are using. Meta Raspberry Pi is providing the machine definitions for Raspberry Pi 4, of course. We're switching to system D. We are making sure that RAUC is going to be installed, enabling UART, and we need to make sure we are using kickstart file, which is containing the right partitions, which matches the RAUC slots. Once we're ready with this, we just need to build an image, flash it on an SD card, and we're ready to go. Our Raspberry Pi can be turned on, and we'll have RAUC on it. The next step is to create an update bundle. For example, let's add Nano, the text editor. We need to build this bundle. And once the bundle is ready, we can either copy this bundle to, let's say, a USB stick and plug this USB stick on the Raspberry Pi to install it from there. Or what I'm doing here on the slides is that I'm turning on a simple HTTP server using Python. And after that, I'm over the air, I'm downloading the RAUC bundle and installing it using the RAUC install command, which has to be executed, of course, on the embedded device, in this case on the Raspberry Pi 4, and to reboot. No matter if it's a Raspberry Pi or another device, the procedure is the same. Here's a screenshot of of the RAUC status after installation on a Raspberry Pi. And there are a couple of important U-boot variables in order to get RAUC working on the Raspberry Pi: the boot order and the boot name left. All the details are available in the user's manual. Actually, RAUC has a very good documentation, so you can find a lot of the answers there if you're getting started with RAUC. Now, the hard part is, based on my experience, the hard part when you are porting RAUC to a new device is to create the script that switches between the slots. Here is an example based on what we have for Raspberry Pi. This is very specific depending on the device, but you need to implement this. And so far, we have it done for at least 4 platforms. The whole point of meta-rauc-community is to provide these scripts and everything out of the box so that you can start with a simple example, and after that to iterate and make it better and make it for your exact use case. As I mentioned, we need to generate RAUC certificates, and the RAUC bundles should be use this generated key and certificate. This is part of the build process. Here is a recipe showing how to create an update bundle. A very simple recipe. You just inherit bundle and define a bunch of variables to define the compatible machine, the slots, and of course, as I mentioned, the key and the certificate. So now the new kid on the block. This is something that has been recently added to meta-rauc-community. This is a sublayer called meta-rauc-tegra. So Tegra is a line of devices by NVIDIA, Jetson. And the particular device that I'm using for this example is NVIDIA Jetson TX2. 2 years ago, last time when we have a Yocto event in person at Leon, I had a presentation with challenges building Yocto images with CUDA support and GCC for NVIDIA Jetson. So I thought that it's going to be a good follow-up to show RAUC working on this device. So the tricky part here is that the NVIDIA Jetson devices have a very specific, each of them has a very specific boot sequence. So we have cboot, which is booting uboot, and then uboot boots the kernel. So I needed to include somewhere the script for the uboot script that switches between the RAUC slots, and I did it by directly patching actually the U-boot Tegra recipe. Here is the patch. Everything is available in GitHub. You can have a look at the technical details after the slide. I'm not going to waste too much time doing a deep dive in the and code reviews. So basically, what you have seen in the previous slide for Raspberry Pi and the way how we switch between partitions with the specific variables which RAUC expects in the U-boot environment has been done in a similar way but different approach here for this device. Just to mention that this is just a demo, and for the demonstration, the U-boot environment is saved to the MMC, as you can see here. This is screenshot from U-boot captured over UART to USB cable. So if you are interested in using this approach for updating NVIDIA Jetson TX2, including the bootloader, beware that there might be conflicts because the U-boot environment is saved to the EMC. And here on this this side, on the right side on the screen, you can see how I have booted the Jetson TX2 with the 2 slots, and the device has been started properly. Something that's very specific for the NVIDIA Jetson devices is that instead of using a WKS file, as I've showed you for Raspberry Pi, this has been done using an XML file where I have described the partitions. It's a standard thing for NVIDIA, but unfortunately not very standard compared to other projects. So everything is available in GitHub in meta-rauc-community, and you can build this image and just boot it on your device as an easy start. Just a little bit of code reviews to explain how the SquashFS and the needed kernel configurations have been enabled specifically for the Jetson Tegra device. I have created a BB append file in a meta-rauc Tegra that extends the Linux Tegra kernel recipe with a configuration fragment. I believe yesterday there was a good hands-on tutorial by Tim who have explained about these configuration frameworks fragments. So I have defined a RAUC.config file, and in it I have enabled all the required things for RAUC to work within the kernel. So I think it's just about time to wrap it up with conclusions so that we can have a little bit more time for questions. As you have seen, RAUC is a secure, reliable, free and open source framework for AB software updates of embedded devices that can be done over the air or eventually with a USB stick manually for some legacy devices, because I know that some people are still interested in this. meta-rauc-community is a community effort to have a layer providing simple examples for RAUC for popular boards. So far, we support 4 machines, and it would be great if in future we can extend the support for more machines. That's why I'm asking you, the community, to step up and help. If you like this project, if you like this layer, and if you're using RAUC, contributions are always welcome. As of the moment, we have Raspberry Pi, QEMU, Allwinner, sunxi, and NVIDIA Jetson Tegra TX2. So here are some useful links. These are presentations done about RAUC over the time. The presentation by Enrico at FOSDEM 2017 was the first time when I've heard about RAUC. He is the creator of the project and the co-maintainer with Jan Lube. After this, the topic about RAUC has been covered on various events, including last year at the Yocto Project Summit, where I've explained in more details, specifically the example for updating Raspberry Pi. So thank you very much. The slides will be available online, and I think we have about 4 minutes for questions.